Hey, welcome back to the Kaggle Titanic series. In the previous video, we looked at how to incorporate some of the categorical variables into our model, and we achieved an improvement of about 12%, which is already nice, so we are on our way up. The next thing I want to look at before we maybe go into depth on some of the other topics is let's check some of the relationships of our variables between our label, just to see, do we have linear relationships, do we see any kind of outliers, is there any data cleaning that we might want to do. So for example, what we can do here is we can say, okay, now we have this feature fair. Let's see how the fair is actually related. So I'm going to use my pivot feature function again. We're just going to pivot on the fair. Is this already sorted? I wonder. It could be. It looks sorted actually, but I'm not sure why it would be. Anyway, we can see that this is a big table with lots of stuff. We should fill in A0, I guess. So every time when survived is a nan, this is a nan, which means no one survived. So, and then we can actually plot, and we want to plot the survival rate. So you can see something like this, which doesn't tell us too much. So it's not a clear relationship. One thing you can say is that in the lower end of the fair, it seems the survival rate is a bit lower, but depending on the sample size here, it doesn't tell us much. And if we look back at the table, you can also see most of these groups contain almost no one. So fair itself might not be the best value. So we could make something like pre-pro fair mp round df.fair. Let's round it. Let's just round it for now, and then we use the. I think I need to include numpy. And then, okay. So here we see we get a little bit bigger groups, but maybe this is not even enough. I mean, now you have to think about, do you care if someone paid $4 or $5 or whatever this is, or do you care whether it was 111 versus 113? Maybe not so much. So you could come up with some more interesting pre-processing. I will just round to the nearest 10. Then we see we get some more fair classes. Of course, while manually doing this, you're also losing information, but I think overall your classifier may just be overfitting if it says, oh, if you paid $10, you definitely survive, and if you paid $11, you definitely died. And then if you paid $12, you survived again. I think this is not necessarily what we want. Now we also have a lot less none classes. We can now plot this again and get a little bit more interesting graph. And here you can see, okay, your survival rate goes up the more you pay. There's a dip here, and it seems to level around 65-ish percent, or maybe 70, somewhere here. This dip is something we could take a look at. This could be, so together with these plots, I usually think it helps to, oops, what's that? Oh, that was not good. You didn't see this. It helps to see the table. And here we can see there were people who paid 510, and all three of them survived. So this is not so. Where are they? They should be somewhere on the right side. It's a little bit shitty that I don't see the x-axis, and I'm not sure why. I tried this plot before the video, and there were no values on the x-axis. Even if we say, for example, reset index, because maybe it doesn't show the values if it's an index, and we plot pre-pro fair and x equals survival rate. Even then it didn't. No No data to plot. This data. What are you talking about? Maybe because there's an all column now. Why is pre-prof here. I mistook these. It belongs this way. So this is essentially the same plot. So I'm not entirely sure why this happens. So I guess this one is actually the 510 and this is the all. Do I manually add this or is it just margins name all, margins false, margins true? Oh yeah, okay. This function is not so nice, I realize. Maybe we want to plot it like this. To remove the all column, got unexpected keyword, I have to re-execute this. What's happening now? New. What's happening? Total. Now it has margins. No. I didn't. Did I change anything? What did I change? Let me see. Okay. Margins false, and then this doesn't work anymore. Margins name all. Okay, I have to check this maybe without the video. It's not that big of a deal. Just remember that this last point is just the aggregation of everything. So we get the average survival rate. So here's one class that only contains one sample too. So you could even say, okay, let's classify everything above 1, maybe even 90, everything above 90 into the same group. So we can do this and then it's maybe not the best way to do it, but apply x and then here x if x smaller 90 as 90, and then I get something like this. There's still the 70. Maybe this is again something funny with these people actually having had whatever interesting tickets. Maybe it's all women, you don't know. So we would have to check how this is correlated with the other features. But technically we could try if our pre-prof fare now is a better feature than before because we made it a bit more linear. While not necessarily having to make everything strictly linear, it's always, I mean, if you just put the feature as it is, logistic regression will basically treat this as a line and just fit a line somehow. Yeah, let's just see if this is somehow helpful or not. And again, if somebody who knows more about logistic regression than me sees this and I'm saying something dumb, please let me know. Just see how the model performs. 79. Let's comment out fair. 78. So across 5 splits, we could make more splits. We don't necessarily care. It's just 78 versus pre-pro fair female. 78. What was the other one? I forgot. 78.2 versus 78.8. So it helps maybe a little bit, but we don't care as much. So for fair, maybe not necessary to pre-process it, but let's check some of the others. Here we're gonna take. So let's start with another variable like how about age? So you can see the survival rate of age is the younger you are, the higher likely you survive. And then there's some more or less average. A little bit higher on the upper end, but this is maybe more or less interpretation. Of course, we can say, okay, this is also very sparse data in each bucket. If we just quickly check how does it look like without, you can see there's like some infants, 1 year, 10 years. I don't think there's a huge difference in this category, so we might even want to round it to 2. Age, oh, sorry, to -1. And here we can see if you're from 0 to 10 years, you have 70% chance of survival. From 10 years, 40, 35, and then it kind of averages out until the like really high ages that we could cut off, because this is just, so this is the average again, and this one is just this one person at a really high age. So in order to make our classifier even more stable against this, we might want to say apply, and then we say let's just see real quick what does the table say. Is this correct? Why is there so many old people now? There's one person here, and then suddenly we have age 90. Somebody there's a typo, I guess. Ah, 177 are not smaller than 90. Is this because we compare against this all? Or we have NaN values or something? Oh yeah, fair than A -1 maybe. Ha, there's our 177. Oh, this is very interesting. So of course we cannot disregard fair and A -1. I don't know. We cannot disregard that there may be -1s. Oh. So let's also print this here. Do we have -1s in fair? No, everyone paid. Or we know that everyone paid, but we don't know the age of everyone. There's actually a class of -1s. So, and if we were to plot this now, this looks a little bit like this. So we have -1, and then from 0 to getting older, your survival rate kind of declines. While here it's just the average, which you can see same here on the right side. And I think overall it would be better to bucket this into, say, something like 0 to x, and then you have some, maybe something that we can put to the intercept, which is the middle bucket here, and then you have above a certain age, with this one removed as an outlier, because you cannot, I mean, maybe there's a pattern that everyone who's 80 and above was safe, but unsure. And for the -1 bucket, if we just now, as this is, put a logistic regression, it will more or less learn that there's this trend here, something like this, and it will just predict more or less the average probability everywhere. But by using this group, by taking this group, for example, and moving it closer to where it belongs, in the sense of, address pre-pro age. This is about 30% of people surviving, which should be somewhere around here. So we could just map them to 20. Just move it to the biggest group. So let's do this. So if you're above 60, then you're just 60. So if x 60, if x above 60, else 20 if x smaller, 0 else x. This is correct. Let me just see. Now we moved the 177 samples here, making this a bit lower, which is then this dip. And then we have again this pattern. So we could now move the 60s to the 20s as well, since they are very similar. I'm actually not sure if this is completely not good practice to do this, but given that we have enough data, this is so little data that we need to be really careful with doing these assumptions. But given that we had a higher sample size, for example, if at your company or something you're running a couple of 100,000 samples a day, then and you see a 30% chance of surviving, then I think you can make buckets of equal survival rates easily without having to worry too much about the error. But actually, if you look at the confidence bounds of the survival rate being 30% with 42 samples and like 13 survived samples, it's gonna be very low or very wide. So I mean, this could be 30 and probably also 40, and yeah. For now, I will make one bucket, which is the like a linear. How do you do this? So as features, I would want to use pre-pro age in a sense that smaller 30 pre-pro age and not as a boolean, but df pre-pro age apply lambda x if x smaller 30, something like this, and then just a boolean. These two, for example, did I put some brackets somewhere? Lambda x. X if x smaller 30. There's something I don't see here. lambda. Oh, yeah, we need an else. Okay, we want to do the same thing with the if test. Oh wait, okay, we don't actually need to do this right now. We just want to check if these features are helpful. Now we need to remove the actual age. So now we improved to 80-ish. So this actually seems to have helped generalize better. And if we check if your age is smaller than 30, your survivability goes down. And if your age is bigger than 30, it goes way down. So if we look at the trend here, this one obviously has some downtrend, while this one is more or less constant. I would say the higher it is, well, this is just a Boolean. So, okay, this is something I should fix. So this is a Boolean. Let's make it Boolean sounding. Is prepro age. Okay. This is okay. So if this one is true, then you get a huge hit on your survivability. But if you're also female, basically if both of them are true, then you roughly intercept in terms of how likely you are gonna survive. The weird thing is that this one, maybe it's not so weird, but the higher this one is, the lower the more likely you're gonna die. Okay, this is also good. I'm just checking if the signs of these variables point in the direction that I expect them to go. And yeah, do we also have prepro age in here? Good. I'm still curious about these embarkment classes. And one, let's just try, see what happens if we add them back in. Doesn't change much, and they all get the same. So I guess what this kind of means that given, or maybe we have to look a little bit more how they distribute it, but given the other variables, they just don't matter so much for us. They get all the same value, which is surprising. So maybe the effect is already modeled by something else, or I'm just not getting it right now. Anyway, this episode is on 23 minutes, so we still have a little bit of time. Let's check. We still have zip, sp, and parch as two variables that I would want to look at. Let's do this real quick. So what we do is we copy the cell, keep the rest, and here we don't do. We want to look at zip sp. Okay. And we zip prepro. Something like this. And we want to plot. Okay. Okay, good. It seems it's always defined. Filling by -1 didn't add another class. we should now actually check out what this variable means, but it appears that if it's 1 or 2, you're much more likely to survive than when it's 0 or higher than 0. So since 0 is not a big deal for us in terms of logistic regression, this just moves the modeling of this risk of not risk of surviving, but this survivability rate to the intercept. We should definitely see that we group the high ones into the lower buckets. So I would definitely introduce a what happened here? How did I do this? Magic. Okay. But actually, I think this feature as it is pretty good. So 0 will be on the intercept, doesn't matter. As soon as it's 1, we are kind of up here and it's just downward. So this is a really nice linear feature. This blip over here is again the all row that I haven't managed to remove yet, and shows us the average probability of surviving. So I think we can leave it as it is. There's not much for us here. We have one more feature to look at, which is parch. Passenger ID is nothing we want to use. Fare, ticket, I'm not sure what we can make up with the tickets. Where is it now? Okay. Parch, prepro, parch, and then we're gonna wrap it up. Okay. Parch, okay. So also always define this, no -1 class, 0 is on the intercept. Most of the samples are actually 0. And these 3 that have some samples in it are all roughly the same. So I don't know, with 5 samples getting 0.6 might as well be the same as this class or this class. And then with 4, 5, and 6, we have like a total of 10 samples, sorry, it's long day. Total of 10 samples here, and all of them didn't survive. No, only one of them survived. I'm not sure how we would want to model that. We could actually say we make it a binary variable where it's either bigger 3 or lower equal 3. So we could try this. Is parch bigger 3 is parch smaller equal 3. Parch smaller equal parch bigger 3, something like this. Why is this here? And then, okay, we look at this now, we are at 80.6 is parch, oh, I did uppercase this now, bigger 3 is parch smaller equal 3. So something like this, 80.7, before it was 80.6, I don't know if this really helped us. So if it's bigger 3, it's not so good, okay. If it's smaller 3, it's actually helping us because we're better than average. This one, the bigger it is, the less likely we survive. This one, the bigger it is, the less likely we survive. So this seems reasonable. So I guess we will just here test. Not sure we need the G at the end. Does this go? Nope, because we don't have pre-pro age, so we need to go back where we actually did pre-pro age. Okay, I will end the episode soon. So now we have it. Oops. Okay, this is good. We want to be here. Okay, this is still good. 80.7. Oh, good. Let's predict here. Pre-pro fair. We also use pre-pro fair. What did we do with fair again? Oh, God. Okay. Zack. Okay. Let's predict and see how well we did this episode. Pending. Oh, I didn't change the string. Okay, actually we got slightly worse. So I wouldn't be too disappointed in terms of how well we may generalize to the data. I think we those were not the best examples, but overall, in my experience, this will help you avoid overfitting on stuff like this. So I don't know. We saw like 20 samples, and the survivability of them was really low. Either there's a pattern here, or this is just some random fluke. So I think going through your features, looking at them, understanding what's happening, which we didn't that much because we have no idea what CBSP means. And then making an informed choice on how you want to group this will benefit in the long run. I also think in terms of coefficients, our logistic looks really well, but people might also say, okay, since there's at least in terms of amplitude, if there's a regularization, it won't tell you exactly what's happening. So one thing we can actually do is we can try to take this model now and try to remove the regularization and start building a model which predicts how likely you are to survive, which we are doing anyway. But we could say, hey, if we are a startup and we want to do insurances for ships, maybe this data set would be something we can use to bootstrap a model, and then we want to build a model which gives us an actual probability of someone surviving or not. Thinking about it now, this could be an interesting kind of project. Let's just see real quick. Can we do... What's the parameter called for regularization? C. I think we have to make C really big to get regularization out of the way. It doesn't change the coefficients much, but now we might be able to use them in actually interpret them as log odds of surviving or not. And then we can say being female makes you twice as likely to survive or something. So I will also read up a little bit on how this exactly worked, because I forgot a lot of this, and then we could dive into this.